Hello, so here we are looking at GCSE Physics for CCEA 2015, and this is Unit 2. Question 1. A student was asked to state a property of electromagnetic waves and gave the answer below. All electromagnetic waves are longitudinal and travel at the same speed in a vacuum. What is wrong with this statement? Well, electromagnetic waves are transverse. That's the big deal. Visible light is a member of the electromagnetic wave family. Name two other members of the electromagnetic wave family. One should have a wavelength longer than visible light and one a wavelength shorter than visible light. Give a use for each. So longer than visible, we could go with something like, say, microwave. And shorter than visible, we could go with something like ultraviolet. Use for microwave would be things like communication, so mobile phone conversation would be an example. And UV is used for things like detecting forged banknotes, so checking dodgy money. Okay, so make sure you think of a good use. If you can't think of a good use, pick something else. Don't pick one that you can't think of a good use for. Okay, so green light has a frequency of 5.5 times 10 to the 14 Hz. The speed of light is 3 times 10 to the 8 meters per second. Calculate the wavelength of green light. You're advised to show clearly how you get your answer, and remember to include the unit with your answer. So this is a wave equation question. And so we need to remember about our wave equation, that V is equal to F lambda. And then we get lambda on its own as V over F, and then we put in some numbers. So if we run that through the calculator, then we get this value, which is like 5.45 times 10 to the minus 7. And that'll be in meters. Part B. To measure the speed of sound, the following experiment is carried out. A single sound is made by striking a metal plate with a hammer, as shown below. The microphone is connected to an electronic timer. When the sound first reaches the microphone, the timer starts, and it stops when the sound next reaches the microphone. So then they ask us to describe the path taken by the sound made by the hammer striking the metal plate. State the measurements that must be taken and how the speed of sound can be calculated from these measurements. You must also state what must be done to obtain a more reliable result for the speed of sound. Okay, so you're going to need to think about what's happening with this sound before you write anything. So the hammer here makes a sound. That'll travel out in all directions, but we're only interested in the sound that's heading towards this wall and back. So you can see here that it says when the sound reaches the microphone, the timer starts, and when it reaches the sound again, the timer stops. So you can imagine sound going out, timer starts, all the way out to the wall and back, timer stops. So bang, timer starts, reflection, timer stops. And you have to basically explain that. So you would talk about the hammer making the sound, it passes the microphone for the first time, this starts the timer, it heads towards the wall, reflects, comes back, and when it passes the microphone again, the timer stops. So in that time, the sound has travelled all the way to the wall and all the way back. So it's twice the distance to the wall. So whatever time is recorded here is the time for sound to travel twice the distance to the wall. So you could call this like D, for example. We could say that this was D. But then when we use it in our equations, we say that, the value of the distance the sound has travelled will be 2D. So it's a basic speed and time experiment. So speed is distance over time, and in our case that would be 2D over the time from the timer. So we would need to measure D and T and substitute into the equation. We would also repeat the timing and take an average to get a more reliable time value. Remember also that if you're asked to measure something, that you mention an instrument. It might seem obvious, but they do expect you to mention the names of instruments you're going to use. So now they showed us this graph. It says the speed of sound in air varies with temperature of the air, and this variation is shown in the graph. And you can see here that we've got some plotted points. We've got the speed of sound in air, and we've got the temperature in degrees C, and it says draw the line at best fit through the plotted points. So get your ruler and do your best to put it through these points. Something like that. So we end up with that. So in the next part we're asked about whether or not this is proportional, and it's not, because a proportional system would be a straight line and also go through the origin. This clearly not going through the origin because it's already reached 0 on this axis, but it's nowhere near 0 on the other axis. So not proportional. We're also asked to find out what speed of sound is at 18 degrees, so we would have to sort of go up here to 18 degrees and draw across to your graph, and you'll find if you do that you get about 343 meters per second. So part 2, is the speed of sound directly proportional to temperature? Explain your answer. Well, for something to be proportional, we would expect a straight line that goes through the origin. And although we have a straight line, it does not go through the origin. So the issue comes with it not going through 00, and so it's not proportional. Using your graph, determine the speed of sound at 18 degrees. Okay, so what we do is, if you have a look at your graph, you zip a 18 degree line up and you take it across and see where that hits the speed axis, and you should find that the speed comes out to be about 343 meters per second. Now we're told that the relationship between the speed of sound v and the temperature T is given by the equation v equals A plus bt. A and B are constants and T is the temperature. Using the graph, what is the value of the constant A? Well, V is being plotted on the y-axis and temperature is being plotted on the x-axis. So this is a straight line where this is the intercept and this here is the gradient, because remember y equals mx plus c is the equation of a straight line. It's just written it in a slightly different order, with this thing here being the y-intercept. So here's our graph, and as you can see, the y-intercept is here at a value exactly halfway between 328 and 332, so that's going to be 330. And we're also asked what is the physical meaning of that value. Well, this is the speed of sound, and in particular here it's at 0 degrees C, so that's what it is. It's the speed of sound at 0 degrees C. And that's that particular question completed.